Anti-roll bar design and material selection for the torsion member for a Formula student vehicle. Abstract: the following study will be dealing with the design procedure, constraints, and limitations that were dealt with during the design of the anti-roll bar system of a Formula student vehicle. Also, simulations with proper forces for torsion on the torsional member to select the best possible material for the torsion member was done. Keywords: FSAE, anti-roll bar, roll, Formula student. Introduction: anti-roll bar, sometime also known as a stabilizer bar or sway bar, is used for the purpose of controlling the roll motion of the vehicle. It provides better stability during cornering. Roll motion referred as to the motion in the lateral direction on the y-axis during which the vehicle rolls around the central axis of the vehicle. Image courtesy RHD Japan. Anti-roll bar increases overall roll stiffness of the vehicle, thus providing a number of advantages to the vehicle and its performance. One of the major advantages is that it provides better traction during cornering the vehicle. Method used: the calculations were done in the following syntax: ride rates, roll analysis, ARB dimensions, and material selection. Ride rates were calculated by first determining the desired natural frequencies of the front as well as rear, but separately. These values were chosen using the general values which have validated after years of experimentation and observation. Natural frequency for the front suspension equals 2 Hz. Natural frequency for the rear suspension equals 2.5 Hz. The reason behind aiming for higher natural frequency in the rear is to compensate for the response delay, since it's always the front suspension which has to act first. Then, the ride rates were calculated for the front and rear individually using the following expression. Here, KRF equals ride rate front, WF equals natural frequency front, WSF equals sprung mass front. Roll analysis: here the first which needs to be calculated is the cog height of the sprung mass, which can be calculated using the following expression here: HS equals sprung cog HT, H equals cog HT, WF equals unsprung weight front. RLF equals tire loaded radius, static, front, were equals unsprung WT. Rear. RLR equals tire loaded radius, static, rear. Sprung WT distribution equals sprung WT front / total sprung mass. Rolling moment, lever arm, equals sprung mass cog HT. Front roll center HT plus, rear roll center HT. Front roll center HT. 1 sprung mass WT. Distribution. Rolling moment per g. Lateral acceleration equals. Here, HRM equals rolling moment, lever arm, calculated above. Now, dividing this value with the desired roll gradient will give us the roll rate required, KF. Roll gradient should be taken between 1.5-3 deg/g for an FS vehicle. Now calculate available front spring roll rate by using the following expression. IJERT 9 is 070675 www.ijert.org. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by International Journal of Engineering Research and Technology, IJERT. www.ijert.org. ISSN 2278-0181. Volume 9 Issue 07, July 2020. Here, KFSF equals front spring roll rate. KRF equals ride rate front, calculated during ride analysis. TF equals track width front. Similarly, by using adequate value, the available rear spring roll rate, KFSR, can be determined. Adding both the front and rear roll rates will give us the total available roll rate. So, ARB must provide equals required roll rate. Available roll rate. Now, to size the front and rear bars, we need to calculate this requirement based on the weight distribution of the vehicle. Multiply this with % load transfer x 100 to get front/rear load transfer. Front roll stiffness, K.F, equals. Here, equals roll gain, 0.5-1 for non-aero FS vehicles. From here, it can be calculated that the rear ARB must provide. Here, TLT/I equals total load transfer during lateral, the difference between the total, rear, and that provided by acceleration. The rear springs. TAV equals average of front and rear track width K, ARB, rear equals KK.F-K.SR. Divide this by the linkage ratio, rear, to get the final requirement. For the front, K, ARB, front equals K.F.K.SF, / linkage ratio, front. Results and discussion. For the method, the whole calculation was done by preparing a spreadsheet to facilitate the calculations, for which the results are shown as followed. It can be seen that the required stiffness for the rear comes out to be negative, which symbolizes that the rear suspension is stiff enough and does not require an ARB setup. Material selection. The following materials were considered. Mild steel AISI 1020 80 GPa shear. Modulus. Aluminum AL 7075 T6 26.9 GPa shear. Modulus. Magnesium alloy AZ31B 17 GPa shear modulus. Although magnesium alloy provides great weight reduction advantage, it is expensive and also for the same thickness, withstands lower stress than aluminum. After running simulations, aluminum was considered as the optimal choice as it provided enough durability, is lightweight, and cheaper than magnesium alloy. The size was determined by comparing the required area moment of inertia to the area moment of inertia of the ARB system torsion bar with desired dimensions. Required area moment of inertia equals required roll stiffness x length of tube / shear modulus. Area moment of inertia for cylindrical tube equals P, 4/32. The following simulation was done by applying 650 N on both ends in torsion that sums up to 1300 N in total. With dimensions OD equals 35 mm. ID equals 15 mm. Conclusion: anti-roll bar torsion member with outer diameter of 35 mm and inner diameter 15 mm was designed to provide roll stiffness of 760.473197 Nm/mm. Acknowledgement by Biswajit Sahoo, School of Mechanical Engineering, Kalinga Institute of Industrial Technology; Chandraneel Pal, School of Mechanical Engineering, Kalinga Institute of Industrial Technology; Piyush Nanda, School of Mechanical Engineering, Kalinga Institute of Industrial Technology. Softwares used: CAD Modeling, SolidWorks 2020. Simulation on CSR 17.2.